Hello, today we are going to be talking about distance time graph, displacement time graph, velocity time graph. In the last class, if you are following, we've talked about the speed, the velocity, uniform velocity, average speed. Okay, but today we are going to be talking about distance time graph, velocity time graph, and displacement time graph. Okay, now distance time graph is usually represented diagrammatically like this, okay, where the vertical axis represents the distance and then the horizontal axis represents the time in seconds, distance in meter, of course. Okay, now the graph for uniform motion, the graph is usually a linear graph like this. Okay, now the slope of the graph is what we call the speed. The slope gives the what? The speed. So it means that speed will be equal to what? Change in distance all over change in time. Okay, that means ds dt. Change in distance all over change in time. All right, so it means if you trace this, you have a figure here. This particular figure minus the lowest, okay, then the change in t is the right minus the left. It will give you dt. Then for a non-uniform motion, you have something like this, okay, distance in meters, and then we have time in seconds. The graph is usually like this. Okay, now the gradient of this is for non-uniform motion. The gradient gives us the what? The slope. The gradient gives us the what? The speed. Okay, let's label this A, B, C. Okay, we have, or maybe we could just see this as the y, and then we see this from this point to this point as x. Okay, here to here as y, change in y. You can just simply say the speed for this, for non-linear motion, is going to be simply dy dx. Okay, now let's check out displacement time graph. It's similar to what we've just done. Okay, we have displacement in meters, usually x, denoted with x, then time in seconds. Okay, for a uniform motion, we have a linear graph still. The slope gives us the what? The velocity. The slope gives us the what? The velocity, okay, which is displacement over time. Speed is distance over time. Okay, if the motion is non-uniform, you have something like this too. The gradient of this also gives us the what? The velocity. Okay, so now let's quickly talk about velocity time graph. Okay, now velocity time graph is more interesting than the other two we have discussed. The reason being that from the velocity time graph, you can find the following information. You can find the acceleration. You can find the following information: the acceleration. You can find the retardation of the motion. You can also find the average speed. And lastly, you can also find the distance covered by the object. Okay, so now we are going to, before we go into problem solving relating to velocity time graph, okay, I would like you to know that the area under any graph, the graph could take the shape of a triangle, the graph could be a square, the graph could be a trapezium, the graph could be a triangle. Whatever shape it takes gives us the total distance covered by the object. Okay, let's look at this problem and let's solve this problem together. But before we do that, let's quickly define what acceleration is. Acceleration is simply the rate, the increase, okay? It's simply the increase. Let me quickly define acceleration. Acceleration, A, is simply the increase in the change in velocity per time. The increase in the change in velocity per time. Okay, while retardation is still the same formula. Retardation, on the other hand, is the decrease in change in velocity per time. Acceleration is increase, retardation is decrease. Okay, now if you want to now define uniform acceleration, what is uniform acceleration? Uniform acceleration is simply when the rate of increase in change in velocity per time is constant, or you could define it this way: when the rate of change of velocity per time is constant. Okay, the same thing with uniform retardation. When the decrease in the rate in change of velocity per time is constant. Graphically, we can represent this. Okay, we have velocity meter per second, we have time in seconds. So now if I want to represent this, we have this, okay. You see, this triangle you are seeing, this force shape, is termed, this is acceleration. Is increasing from 0 to a particular figure. Let's say this figure is 30. Okay, increase in change in velocity. While this one, let's say from 30 it drops down to 0. This is what? Retardation. And this is termed decrease in what? In velocity per time. Now if you get to this point, you see that it is uniform. Okay, there is no change. The velocity is constant at this point. This particular spot or this particular point is termed uniform velocity. Uniform velocity. Now let's check out this example. We are going to solve this problem, demonstrate it on velocity time graph, and then see how to solve problems like this. So let me quickly wipe this part of it so we can solve that problem together. A car starts from rest. Before when you see a problem of velocity time graph, the first thing you should do is draw your velocity, the graph itself. The graph itself. So we have velocity meter per second. Please, it is important you label and then put the units. Then you have the time in what? Seconds. Okay, after you have done this, then you follow the question gradually. A car starts from rest and accelerates uniformly until it reaches a velocity of 30 meters per second. So usually we represent velocity on the vertical. We represent time on the horizontal. So the car starts from rest. So if this is 0, the car starts from rest until it goes to a particular velocity. Let's say the velocity, according to the question given, is what? 30 meters per second. You don't have to repeat the meter per second because we've already done that. Okay, done it tightly. Okay, after what? 5 seconds. So it took the acceleration 5 seconds. So we'll bring it down here. You write 5. We don't have to write that seconds again because we've already done that here. So we'll continue with the question. It travels with uniform velocity. It travels with uniform velocity for 15 seconds. I told you before that uniform velocity is usually represented with a straight line, meaning there is no change, there's no increase, there's no decrease. It's constant. So it maintains this speed for another what? 15 seconds. Hello. We are not going to be writing 15 seconds here. Okay? Instead, we'll do a summation. 15 plus 5 will give us 20. We will not be writing 15 here. Because if you write 15 and you want to find change, 15 minus 5 will not give you the value here. So 15 plus 5 will give us 20. Let's continue the question. And is then brought to rest in 10 seconds with uniform retardation. Okay, it's brought to rest. So it means from this particular velocity, which is 30, it was brought to rest. Rest is definitely 0. So it was brought down to rest. Okay, so let me shift this, let me move it a little so I will have my information clearly stated. In 10 seconds, I told you before, we are not going to be writing 10 here. So we'll do a summation again. 10 plus 20 will give us 30. So we'll register 30 here. Then, of course, time in seconds. So now let's go to the question. The question says, determine the acceleration of the car. Determine, the A says we should find the acceleration of the car. And what is the formula? Acceleration is simply what? Increase in velocity per time. So we have V minus U all over T. Of course, by now we know what all these letters are representing. A for acceleration, V for final velocity, U for initial velocity, and T is for time. Okay? Now, it started from here. For acceleration, it started from here. It ended here. Okay? So, here will be our final and here will be our initial. And this is the time. Okay? 5 minus 0 is the time. So, if final is 30, we have 30 minus 0 all over 5. So, 30 minus 0 will give us what? 30 all over 5. 30 all over 5 is equal to what? 6 meters per second squared. 6 meters per second square. If you don't like this formula, like I told you that the slope also is equivalent to acceleration. So this is slope, this is a triangle. We can do dv dt. Okay, you can use, or another method you can say, or slope is equal to what? dv dt. And what is dv? It's the same thing here. 30 minus 0 all over 5 minus 0. We'll still come back here. The B part. The B. It said the retardation. Okay, the retardation is simply minus A is equal to V minus U all over T. Okay? Minus A representing retardation. Meaning negative acceleration, final velocity, initial velocity, and then time. Let's come back to the graph. So now, retardation starts here and ends here. So it means this is our initial for retardation, and this is our final for retardation. So if we put this in this formula, we'll come to this. Our minus A is equal to, our final is what? 0 minus, our U is what? 30 all over T. What is the T? What is the time it took this deceleration or retardation to take to happen? 30 minus 20, which is equal to what? 10. Okay, this will give us what? Minus A is equal to what? Minus 30 all over 10, which is equal to what? Minus 3. Okay, meter per second squared. Minus we cancel minus. Our negative acceleration or retardation is equal to 3 meters per second squared. Now the C, the distance covered after 5 seconds. They are asking us to find the distance covered after 5 seconds. So, like I said before, I said the shape gives the distance. Okay? If the shape is a triangle, just use the area of that shape to get the distance. If it's a trapezium, use the formula of trapezium to find the what? The distance. Okay, the area formed under the graph gives the distance. Okay, since this is the area under that 5 seconds, what does it look like? It looks like a triangle. So if you are going to be using the area of a triangle, which is the area of a triangle is equal to what? Half base times height. Half base times height. Okay, so we have distance covered after 5 seconds. Covered after 5 seconds to be equal to half. This is our base. Our base is equal to what? 5. So we have times 5, and this is our height. 30 minus 0 is equal to what? 30. So we have this, right? We have 5 times 30 is equal to what? 150 divided by 2. 150 divided by 2 will give us what? 75 meters. So we have 75 meters, okay, as our distance covered after 5 seconds. Okay, now let's go to D without much ado. The D part says the total distance covered. Now, it's not saying after 5 seconds, either is it saying after 20 seconds or 30 seconds, the distance, total distance. So it means the total distance covered. Okay, so it's going to be the area under this graph that we have. Okay, now looking at this shape, it looks like a trapezium, but if you are confused, however, you don't know what shape your diagram formed, you can split it. You are permitted to split. Okay, now if I'm to split this, I have a triangle here, A. We have another one here, B. I think this is a rectangle, and then we have another one, C, another triangle. This area plus this area will give me the total distance covered. But if you want to solve straight, this is a trapezium. We can use the area of a trapezium to solve. We'll still get the same answer. So let's do this. I think I will try using this formula, and then I'll use the formula for trapezium to solve. D, the total distance covered. So I'm going to use this method first, then we'll use the area of trapezium. Now, we have already found the A to be 75. This one, after 5 seconds. We've done that. So I'm not going to be repeating it. So we'll do this one. We have already determined A. A is equal to 75. Okay? So now the area of B is what we'll be looking for. Area of B, which is equal to what? Length times breadth. Length times breadth. So the length, 30 minus 0 is what? 30. And then the breadth is 20. This is the breadth. 20 minus 5 will give us 15.